electric current. That is the reverse effect of producing that current. So current producing the magnetic effect. By using that magnetic field, we can produce the current. That is the reverse effect. That was produced by other. The series experiment was conducted by the Michael Faraday. So in the year of 1831, so in the USA, he simultaneously the other one scientist, Joseph. So he also attempted the successful discovery of the phenomena called electromagnetic induction. So before going to see this lesson, we have to recall the third lesson. In that lesson, we have studied that electric flux and magnetic flux. So electric flux is we studied in the first lesson. Magnetic flux we studied in the third lesson. So what is meant by magnetic flux? So magnetic flux is the magnetic lines of force which is originated from the north pole and terminates from the south pole. So that is the magnetic flux. That magnetic flux means number of lines passing through a given area is called magnetic flux. Okay. So now here we are going to recall the magnetic flux. So electric flux already we know that magnetic flux is that's also we already know that. So now we are going to see the magnetic flux. So magnetic flux. So what is magnetic flux? See that in magnetic flux, the number of lines passing through a plane of area A perpendicular to the field is called magnetic flux. See, that's the closed area. It is perpendicular to the closed area, that is magnetic flux. That is denoted at phi. So that's called the magnetic flux. Or you can derive that phi equal to B into A. The flux through the plane is given by phi equal to BA cos theta. It's a dot product. So we have to multiply the BA. That is called the BA cos theta. Here that's a close. You can see the different angle of the closed surface area. That magnetic flux is perpendicular to the closed area. So the number of lines passing through a given area is called a magnetic flux. Always that magnetic flux of the closed surface area is 0. So always the total magnetic flux of a closed surface area is 0. But that open area is not a closed surface means it has the value. So unit of magnetic flux is Weber. Suppose you are taking that a curved surface, it is the magnetic flux is looked like this. Okay, all the magnetic lines of force is perpendicular to the surface. So it is not a closed surface means definitely it has the value. Suppose it is a closed surface, that magnetic flux is total magnetic flux of the closed surface is 0. Okay, and it's a very important quantity for the electromagnetism. And the open surface has some value. That value we can calculate it from by doing the integration. So next we are going to see that Faraday's experiment. So Faraday discovered the electromagnetic induction. So now we are going to see that how Faraday discovered that magnetic flux and what is the Faraday's experiment. So in that Faraday's experiment, he takes the one galvanometer and one coil and one ball magnet. So using that, we are going to explain the Faraday's experiment. So galvanometer is connected to the cylindrical coil C. So G is the high sensitive moving galvanometer. G is the galvanometer. C is a cylindrical coil. It's a conductor. So wounded like this. So it's called coil. And galvanometer is connected to the coil. It's a bar magnet. So two poles are there. So when magnet is moved inside the coil, the magnetic lines of force is cut by the coil shows the deflection in the galvanometer. So when you withdraw the magnet, again that shows the deflection, but in the opposite direction. So see that's a bar magnet. Bar magnet, when it is moving towards the coil, a flow of current is induced in the galvanometer. When you withdraw from the coil, again that current is produced in the opposite direction. So this experiment was done by the Michael Faraday. So see that galvanometer shows the deflection. The deflection indicates that when magnetic lines of force is cut by the coil, a flow of current is produced. Due to that, the induced EMF in the coil. So that's called induced EMF. Due to that induced EMF, they are producing the current is called induced current. When we change the polarity, again inserted into the coil, it flows the current in the opposite direction. So when you withdraw from the magnet, from the coil, again the direction is opposite to the direction. So instead, suppose when North Pole is moving, its clockwise tone means South Pole. We turn the coil into the magnet into south side. It's moving in a anti-clockwise direction. So when you change the polarity of the bar magnet, that flow of current also changes. So this experiment was done by the Michael Faraday. So now we are going to see the Faraday's law. So by using that experiment, he can give the two laws, and that experiment he produced the three illustrations. So now we are going to see the illustrations and how he explain the laws. So electricity and magnetism. So that is called electromagnetism. So we can convert that electricity into magnetism, magnetism into electricity. That's why the two things are reversed to each other. So now you can consider that the battery is connected to the conductor. So when current flow through the conductor, a magnetic field is around it. So this was discovered by Hans Christian Oster. So when you place the compass near the wire, it will show the deflection. So this was discovered by Hans Christian Oster. Already we know that we studied in the third lesson. Okay. So these principles are used in that electrostatic motor, that is induction motor. So now you see that experiment. So Faraday's law. From that experiment, you are going to conclude that the Faraday's law. So magnet is moving inside the coil, and EMF is induced. See the direction of the galvanometer. So when you insert it, it's moving in one direction. When you remove it, it's moving in opposite direction. See that? Suppose you are changing the polarity of the magnet, so it is changing the direction. So that is the basic principle of the generator. So it's also called as a generator rule. See the deflection. So the magnetic flux is cut by the coil and EMF is induced. So it's a flow of current in the galvanometer. So see that moving in a one direction. Etc. From the coil, it's moving in the opposite direction. Then it comes to zero. So right side, then etc. It's moving in the left side, and comes to the zero. Without that, there is no relative motion between the coil and magnet. There is no deflection in the coil. Okay. Then see that another one thing. See the bar magnet, now it is in the south pole. So moving towards the coil, see the direction of the galvanometer, it is opposite direction. So initially north side means it's moving the right side, south means it's moving the left side. When you withdraw from it, it's moving in the right side direction. So it is the opposite direction. So moving insert, it is one direction. When you withdraw from the magnet from the coil, it's moving in the opposite direction. So when you change the polarity, the direction changes. So that was discovered by Michael Faraday. So experiment was done by the Michael Faraday. So from that he concluded the two laws. So you can able to see the direction of the galvanometer, that indicating the flow of direction, which direction that current is flowing. Now you can see that two coils. That one coil is connected to the battery. That another coil is connected to the galvanometer. C2 is connected to the battery. So when the current flows through the coil, a magnetic field is produced. So C2 coil, it has a magnetic field. So magnetic field is produced. So see that how the magnetic field is produced. Now the coil C1, the two things are stationary. There is no deflection in the galvanometer. So the two coils are separated by the distance. So there is no deflection in the galvanometer. So now we are going to move the coil C1 towards the C2. Now the magnetic lines of force is cut by the coil. See that it shows the deflection. When you move away from the coil, again it will show the deflection in opposite direction. See that it's moving in the opposite direction. So again, finally it comes to rest in the zero. So whenever the magnetic flux is cut by the coil, EMF is induced. When the two coils are separated or in a rest position, there is no EMF is induced in the coil. See, now C2 is moving towards the C1. Again the coil is cut by the magnetic flux, that EMF is induced. That we can see in the galvanometer. After connecting the two, facing very close to the two coils, there is no deflection. Whenever there is a relative motion between the two coils, the magnetic field is, and you see that when it is moving, the galvanometer shows the deflection. So it's a different kind of experiment. How we can do that experiment by using the bar magnet and the two coils. Now here the coil is used as a bar magnet. We can change the flow of current in the coil also by interchanging the battery. Now we can do the same experiment, but now this time we are going to connect the key. So the two coils are placed very close to each other. That one coil is connected to the battery. When the key is connected, the EMF is induced. After connecting, there is no EMF. When you open the key, it will show in the opposite direction. See that? When you connect the key, it shows the deflection. After that, there is no deflection. When you remove the key, it shows the deflection in the opposite direction. After that, it will come to rest in the same. See? So, initially, the flow of current and the final current, when you remove the current or given the current, you can change the deflection. And when the other rod is placed between the two coils, the magnetic flux of the coil is increases. See that after inserting the magnet metal, see the key when it is open or closed, the deflection is more. When before placing that iron rod, it is placing between the C1 and C2, the deflection is increases when you place the iron rod between the C1